Hello everyone and welcome to another video. Today I would like to talk about perhaps the most important probability distribution function, namely the Gaussian distribution function. Now, the Gaussian distribution function or probability distribution function, you may have heard this also referred to as a normal distribution, just because it is so common and quote-unquote normal that it is it's given this also moniker. In fact, normal distribution might almost be more prevalent than the Gaussian distribution, but they both mean the same thing. What they're both talking about is a probability distribution f of x, which is given by this expression: 1 over sigma times square root of 2 pi times e to the minus 1/2 times the quantity x minus mu all over sigma. This entire quantity is squared, and then that's the end of the exponent here. So in this case, these parameters mu is the mean, and sigma here is the standard deviation. Okay? So this is what this function looks like. Let's make a couple of observations about this function. Some things to note. Like we said earlier, mu is the mean, right? Sometimes you might also hear this referred to as the expectation. It's basically where most of the probability is centered around. And then sigma, like we said, is the standard deviation. But sometimes you'll see people want to talk about variance, which is just nothing more than sigma squared is the variance. So really this is pretty simple, that standard deviation and variance are basically, in this case, referring to the same thing. One of them is just the squared or the square root of the other. So I wanted to point this out because I guarantee you this is one place where it's super easy to get mixed up. Are you talking about standard deviation or are you talking about variance? The relationship is very simple, but again, I just want to call it out specifically here because different authors will use different notations. So let's just be aware of that. Okay, another thing to note, this constant factor right in front, this 1 over sigma times square root of 2 pi, is it's just a constant, right? Because sigma is a constant and pi is obviously a constant, right? And what this is, it's sometimes referred to as the normalizer. Let's just write that down. So sometimes referred to as the normalizer. And its main job is, again, if you think about this, we claim that this is a probability distribution function. So by the time I integrate this from x is minus infinity to positive infinity, the area underneath the curve is 1. And this normalizer just guarantees that the overall integral is 1. So you can kind of think of this as just being, it ensures that the integral from minus infinity to positive infinity of f of x dx is equal to 1. Okay? The other thing to maybe note here, 3, this is going to be important later here, but f of x is symmetrical about x is equal to the mean. Okay, and we're going to look at this in a couple of different plots. We'll go run to the computer and plot this function out, but you'll see that it's basically symmetrical about the vertical axis of x is equal to mu. Okay. The other thing that we can note is that the exponential term actually is going to make this thing decay fairly quickly as you move away from the mean. So the exponential, right, like any exponential, oh, I spelled that wrong, exponential, right? The exponential dies / decays fairly quickly as x moves away or goes away from mu. Okay? And we notice here that this term sigma is actually a knob that can be used to determine how quickly or slowly that decay occurs. So sigma tunes or influences the rate of decay, right? Okay? So with that in mind, I think maybe it should be a time that let's run over to the computer and maybe like Mathematica, and let's plot this function for a couple of different values of mu and sigma, just so we can understand what does it look like and how does it behave. All right, so here we are in Mathematica. So let's go first and define the Gaussian / normal distribution function. And we said that was f of x, and it was also a function of the mean and the standard deviation. And the function was 1 over sigma times 2 pi to the 1/2, right, times e to the minus 1/2. Whoops. Let me put the minus in front there. All right, times the quantity x minus mu all over sigma. This quantity was squared, and that ended the exponential. There we go. So here's my Gaussian function that we talked about. Let's go ahead now and how about plot this for various mu and sigma values, just so we can understand what it looks like. So let's just do, how about one of these? Plot, how about, let's try a mu of, how about 0 and a standard deviation of 1. Okay, and let's plot this between, I don't know, how about minus 5 to 5. Let's make the plot style, let's make this red, okay, and shift enter. So here we go, and you can kind of see that this Gaussian distribution looks kind of like this this bell shape. In fact, this is one of the common names. You may hear the Gaussian distribution or the normal distribution referred to as a bell curve, due to this bell-like structure. However, it should be noted that other distributions, such as the Cauchy or the student T and the logistic distribution, also display similar bell shapes, but the Gaussian is special. So this is what it looks like. So we see that it is centered around the mean, right? In this case, it was 0, and it indeed looks like it is symmetric on either side of that mean. Tell you what, let's call this plot, how about P1? Because I want to compare this and make a couple of other plots. So let's actually, how about just copy this and paste it down here. We'll make another plot P2, and let's just change the mean and the standard deviation just so we can see its effects. So how about let's move the mean, instead of 0, let's move the mean out to, how about 2? And let's have the standard deviation and make it a standard deviation of 1/2 instead of 1, and maybe we'll plot this one in green. So okay, so here you go. You look at it. Oh, it kind of went off the page. Let's go ahead and plot range all this thing so we can see the whole thing. And here's what this other Gaussian looks like. We'll plot multiple of these together on the same plot just so we can compare. So let me make one last third plot. And here, let's move the mean. How about to the negative side? How about -1? And let's increase the standard deviation to, say, 2. And let's finally call this one red, green. How about we'll plot this one in blue? There's P3. Okay, so now let's plot all of them together so we can see and compare. So I want to go show P1, P2, P3, and let's have the plot range be all so we can see everything together. Okay, so if I shift enter that, here we go. So you can see all three of these Gaussians compared one another with each other. So the red one we saw was our Gaussian with mean of 0 and standard deviation of unity, and you see it's centered around the mean. The green was our next one, right? So we moved the standard deviation, or sorry, excuse me, we moved the mean to 2, and then we decreased the standard deviation to 1/2. And we see what that does is it makes the Gaussian more narrow or spiky, I guess. And again, to keep the area, remember the area underneath each one of these curves has to integrate to 1. So we see that it gets spikier, it gets narrower, but it also gets taller, right? And finally, contrast that with our third example, the blue one, where we moved the mean to -1. So again, we see that it is still symmetrical about the mean, but since we increase the standard deviation, what we're doing is we're increasing the spread, or the, well, I guess the variance, right? We talked about how the variance is the standard deviation squared. So by increasing the standard deviation, we increase the variance, and we flatten it out a little bit, right? We make the tails of this longer. So again, the area underneath the curve is 1. So if we're going to flatten and smooth that same amount of area out, the Gaussian has to get shorter. So hopefully this gives us a good feel for how the mean and the standard deviation affect the Gaussian. I'll show you one other thing before we jump back to the board, since we're already sitting here in Mathematica. I want to just make a note here, that Mathematica has the normal distribution function to represent a Gaussian. So what you can do is you can say normal distribution, and you pass it the mean and the standard deviation, and shift enter, and you can see actually by itself this isn't terribly useful because it's giving us actually Mathematica stores this as a fairly complicated and a versatile object here. So we need to use this. So we're going to say by itself this isn't useful, but in conjunction with the PDF function in Mathematica, whoops, I spelled function wrong. Let me fix that. This is what I love about mathematics. Got a spell checker, right? We can obtain the functional description. Meaning what I can do is, instead of just writing down normal distribution, let's wrap this thing in a PDF call and say this is a probability distribution function with respect to x, and now this is going to basically be another representation of the Gaussian. So you know what? I think we called our original Gaussian f, so let's call this, how about f2 of x, sigma, and, or sorry, we did it in the opposite order, mu and sigma, right? I got to make sure I want the order to be the same. So we see that f1, or sorry, f, I guess what we called earlier, right? This was what I defined. Come on, mu and sigma. This is what we defined earlier. This is going to be the same thing as using the Mathematica version to go ahead and represent the same thing. And we see that they're true. Okay, great. So with that being said, let's jump back over to the board and play a little bit more with this Gaussian. All right, so now that we know what a Gaussian or a normal function looks like and behaves, I'd like to talk about something that's closely related, and that's called the error function. Okay, so to understand the error function, let's go ahead and consider a Gaussian or a normal with a mean of 0 and a variance of 1/2. Okay, and since the variance is a half, right, obviously the standard deviation is just square root of 1/2. Right? So however you'd like to think about it, okay? So if that's the case, all right, we said that in this situation, the Gaussian distribution or the Gaussian function, it just looks like this. 1 over square root of a pi times e to the minus x squared. Okay, so that's what this Gaussian looks like. Now, what we would like to do, we know that we can kind of plot this out, right? If we wanted to draw this, we know now that what this function is going to look like, it's going to be centered around the mean 0, and it's going to have a standard deviation of square root of 1/2. So I don't know, it's going to look something like this, right? And it's going to be symmetrical about that. Right? Okay, so now what I would like to do is I would like to compute what's the probability that a sample that's drawn from this distribution falls between positive x and minus x. Right? And we know from the discussion of probability distribution functions is the way to compute that probability is that's the integral of the probability distribution function, right, between the values of interest. So it's this area under the curve, right? So what I want to do now is, let's write that down. So I want to compute the probability that a sample falls between the range minus x to positive x, right? Okay, so then in that case, all we need to do is we can write, okay, I want the probability that some sample z is in the range of minus x to x, right? Well, all we have to do is we need to integrate from the minus x to positive x, the function f of, I guess we got to change the variable of integration. Let's call this f of t, right, dt, right? And the probability distribution function here is this Gaussian that we are investigating, so let's just substitute that in. So it's minus x to x of 1 over square root of pi e to the minus, and again we're changing the variable of integration so I don't mess up the difference between the thing we're integrating and the limits of integration. So we end up with this, right? Okay, So let's go ahead, and one thing that we can note is, if you think about this long enough, I'm integrating this function here, and you notice that this function, since it's symmetrical on either side, right, the area that is between minus x and 0, right, this area is the exact same as the area between 0 and x, right, since we know that the Gaussian is symmetrical. So actually, what you could do is you can actually write this as, well, I can break this thing up, and I can say that this is actually integral from integral from 0 to x, and then I just need to multiply it by 2 in the front. So here we go, 1 over pi e to the minus t squared dt. Right? That's the same thing because of this symmetry argument that we just had, right? Okay. So let's see, what can we do? This now is a little bit odd. We can't actually analytically compute this integral here. Sure, you can maybe move this constant out here, but this e to the minus t squared dt is actually not able to be analytically computed. So what ends up happening is, let's call this entire function, this is what's known as the error function, or sometimes abbreviated as ERF, or lowercase erf. Okay? So this whole thing, let's call this ERF, or the error function of x, right? Which we said basically measures the probability that a sample falls between minus x and x from this very specific Gaussian with mean of 0 and variance of 1/2. So this right here is the definition of the error function. It's basically this integral that we can't easily compute. That being said, what happens is a lot of computer packages, like MATLAB or Mathematica or actually any other language usually, will provide an implementation, a numerical implementation of what is the error function. So with that, we can use that numerical value of this integral to understand what does this Gaussian look like, okay? So tell you what, let's do a couple of things. Let's run over to Mathematica again and again try to compute this integral and show that it's just going to say that this is the error function. All right, so just continuing on with our Mathematica notebook, let's scroll down and get a little bit of white space. And what we would now like to do is let's go ahead and, again, like we said, consider the normal slash Gaussian with mean of 0 and standard deviation of, what was it? It was 1/2 to the 1/2, square root of 1/2, right? So we already know what that was. I already have my function f to do this, so we can go ahead and just write this like such. And we can get our Gaussian function. I mean, heck, if we wanted to, we could plot this thing just to see what it looks like, but we already know that this looks like a, yep, here's our Gaussian centered around 0. Okay, and now let's go ahead and try to do what we did on the board, namely compute probability that sample falls between minus x and positive x, right? So we said that the way to do that is I just need to integrate, whoops, I want to integrate f of, well, I guess it was this Gaussian function here, right? Let me copy this so I don't have to retype it all. Integrate this and, well, and I guess we changed the variable of integration here. So let's go from t, and we're going to say t goes from minus x to x. Right? And if I shift enter that, look at that. Like we said earlier, Mathematica just says, oh, you know, I know what you're doing. You are looking for the error function. So here's the error function. So let's go ahead and maybe what we might want to do here is let's go ahead and plot the error function. Okay, just to show that Mathematica has a numerical implementation of this function. So I can go ahead and plot this error function, ERF, and let's make x run from the same range that we did this plot of the Gaussian up here. So let's say from -5 to 5. Okay, and shift enter. And here you go. So you see it can clearly plot this. It has this function defined. And we should be pretty much ready to go. One thing I should maybe mention is that this error function, it is not a cumulative probability distribution function, right? Because remember, all this says is what's the probability that a sample falls between minus x and x, right? A cumulative distribution function is going to tell us the probability that a sample falls between minus infinity and some arbitrary x. So now that we're armed with this information about the error function, we can actually go ahead and define a proper cumulative probability distribution function for the Gaussian. So let's jump back to the whiteboard and do that now. All right, so now we're able to talk about the cumulative distribution function of our Gaussian. And remember, we said that the cumulative distribution function, capital F of x, right, is, this basically told us what's the probability that a sample from this distribution will fall between minus infinity and x. So all we need to do here is integrate the function of interest, right, oops, I guess dt again, I keep messing up this variable of integration here, right? From minus infinity to positive x, okay? So in our case, we want to do a Gaussian. So again, all I need to do here is plug in this f, which is our Gaussian, which was what? It was 1 over sigma square root of 2 pi times e to the minus 1/2 times t minus mu all over sigma, this entire thing squared, dt, okay? So this is going to give us a cumulative distribution function. However, again, we run into the same issue where this is, I mean, this integral is ugly. So actually, you know what? I really don't want to do this by hand. Let's, sorry for jumping back and forth, but let's go back to Mathematica and have it go ahead and just perform this integral for us. All right, so continuing on with our notebook, let's go ahead and compute the cumulative distribution function. Okay, and we call that capital F of x, right? And we said that, all right, so capital F of x is also going to be a function of mu and sigma, so let me go and put those in right now. We said that that was just the integral, so we're going to integrate f of x, mu, and sigma, right? So we're integrate our Gaussian distribution, and we're going to go from x is minus infinity to x. Oh, sorry, whoops, and I keep doing this. Let's change the variable of integration to t so we don't mess this up. There we go. Okay, so this is what we had on the board. So we can go ahead and integrate this, and I'll shift enter this. It's going to think for a little while because, like we said, that integral is not the nicest thing. So we get a conditional expression. A couple of things are a little odd. Let's simplify. We know the standard deviation is always positive, right? So what we can do is we can simplify this expression and say, hey, Mathematica, I know that the standard deviation is always positive. And under that condition, this actually simplifies quite nicely. And we end up, we see, oh, hey, look, our good old friend, the error function, showed up again. So here, this is a better representation of the cumulative distribution function. As a quick side note, you know, Mathematica also has the, we saw this earlier, the CDF function, which was cumulative distribution function. So we could go and use this in conjunction with the, we already saw that there was the normal distribution, right? This function, which was, oops, sorry, with mu and sigma, right? We said that this was this interesting kind of complicated object which can be used with many other functions. So we earlier used it with PDF. Let's now use it with CDF. And say with respect to x. And what this is this should be another representation of the cumulative distribution function. Let's call this, how about f2 of x, mu, and sigma. So here's another way you can also compute the cumulative distribution function of the Gaussian. Now, notice that we did not get the exact same answer, and that's because you'll notice Mathematica decided in this case to use the IRF-C. IRF-C is the complementary error function, and they're actually related quite easily. So IRF-C of x is nothing more than just, oh, come on, 1 minus IRF of x. So they're basically very similar. You can see why it gets the name complementary, right? And in fact, we can show that these are the exact same thing, right? So I can just test that f, or big F and big F2, these should be the same thing. And again, let's go / simplify and just say, hey, keep going. Whoopsie. Why did that not come out to be the same? Did I mess something up? Did I switch the order? Let's try. How about full simplify? Okay, there we go. Okay, maybe I just didn't ask it to simplify far enough. Okay, so full simplify. It is indeed true. Okay, so now that we've got the cumulative distribution function, it's this or this function, however you'd like to express it. Let's go ahead and how about plot various f of x, or I guess plot f of x for various mu and sigma. All right, just like we did earlier. Okay, so how about let's make a P1 and we'll say plot f of x And again, let's how about do a mean of 0 and a standard deviation of 1. And let's plot this x from, I don't know, how about -5 to 5? Okay, here we go. And again, here maybe let's make this thing red. Plot style goes to red. Okay. And then what was our other one? I think we had P2 was, what do we change it? Let me scroll up here. I'm trying to remember what these other Gaussians were. We said, okay, 0 and 1, and then the other Gaussian we looked at was, okay, a mean of 2 and a standard deviation of 1/2. Okay, let's do that. So how about a mean of 2 and a standard deviation of 1/2? And I think we made that one green. And then finally we had a blue one. Oh, sorry, this should be P2. Okay, and then I think we made a blue one earlier, which was a standard mean of -1 and a standard deviation of 2. I think that was, okay, red, green, blue. Okay, there we go. Here's all of our different Gaussian cumulative distribution functions, and again, let's plot them all together. So I'm going to show P1, P2, P3, plot range, all just so we can see what they all look like together. Okay, so here we go. And again, all these is, right, it's nothing more than the integral of these Gaussians, right, from -infinity up to x. So again, this has your standard interpretation of a cumulative distribution function, right? It tells you the probability that the sample falls between -infinity and the value you're interested in. So if we're interested in seeing how often does a sample fall between -infinity and say positive 2 here, all you would have to do is just follow this up, and we see that, okay, your Gaussian, which was with a mean of 0 and a standard deviation of 1, that was the red curve. That's almost 100% that all of the samples fall between -infinity and 2. And likewise for the other ones. For the green one, right, that was the mean of 2 and a standard deviation of something else. And actually, this is interesting. If you follow this up, I think this comes out to be exactly 1/2, which makes sense, right, because the Gaussian is evenly distributed around the mean of 2. And likewise. Okay, so this gives us a good idea of the of what the cumulative distribution function for a Gaussian looks like. Let's jump over to the whiteboard and continue our discussion. Okay, so at this point, I'd like to introduce what's called the standard normal distribution. And all this is it's a distribution, f of x. It's a Gaussian here, but it has a mean of 0 and a standard deviation of 1. So maybe we should just write that down. So in this case, the mean is 0, the standard deviation, and I guess in this case, it's the same thing as the variance. Both of these are 1. Okay, so what this looks like is, again, if you just plug it in to our expression, it's 1 over square root of 2 pi times e to the -1/2 x squared. Okay? And this here is our standard normal distribution. And in fact, this is so important that sometimes it's given a special name. Let's call this thing lowercase phi of x. Okay? Similarly, if we have our standard normal distribution, you can get our standard cumulative distribution, which again, all it is, it's your Gaussian with mean of 0 and a standard deviation or variance of 1. But now we're just going to integrate this thing. So this is, right, big F, capital F. It's just going to be nothing more than the integral from -infinity to x of the standard normal distribution, right? E to the -1/2 x squared. Again, I always want to put x instead of t, right? But here's our variable of integration. That's our upper limit of integration. Okay, so this here is your standard normal, standard cumulative normal distribution. And again, it is important enough that it's given a special name, and again, to make notation confusing slightly, instead of lowercase phi, let's call this uppercase or capital phi of x. Okay? So those are the two definitions. Now again, we just saw in Mathematica there's an easy expression for a cumulative distribution function of a normal. So if you just went ahead and plugged it in, what you would end up with here is you would see that capital phi of x is just going to look like 1/2 times 1 plus the error function of x over root 2. So again, what's beneficial about this description of it here, as opposed to the integral description, is again, Mathematica and any other computer tool will provide a numerical implementation of ERF, so we should be able to compute the standard cumulative distribution function, no problem here. Okay? Now, the only issue here is I don't really necessarily want a standard distribution, right? Because the standard cumulative distribution function is only with mu equals 0 and a standard deviation of 1. What about for an arbitrary standard deviation and variance? Let me see. Let me just erase these two so I can get a little bit more space on this side of the board, okay? So let's pose a theorem here. Let's call this, how about Theorem 1? Okay, Theorem 1 here is basically going to relate a standard cumulative distribution function to basically an arbitrary one. So what this says is that the cumulative distribution function let's call this thing, again, capital F of x, right, of any normal distribution. So in other words, this has an arbitrary mean and standard deviation here. This is related to the standard cumulative distribution function, which we called capital Phi, right? Via or by, okay, if this is what I'm interested in, right? I want the cumulative distribution function for an arbitrary mu and sigma. Well, all that is, it is the standard cumulative distribution function, which we already have here, but instead of passing in x as the argument, it's x minus mu all over the standard deviation here. So in this case, mu is the mean of f of x, right? And again, sigma is the standard deviation of your arbitrary distribution, okay? So why this is so helpful is that, okay, if I know I've got a normal distribution with a specific mean and a specific standard deviation, but I want to know its cumulative distribution function, I could use the standard normal distribution, which has a convenient expression and implementation using the error function. So I can basically get this function through effectively two calculations. So the proof of this is really dead simple. It's just dead straight up substitution. So let me just jump over to Mathematica and substitute this in just to convince you that I'm not pulling your leg. All right, so to prove this, let's first go ahead and define the standard cumulative, I keep spelling this wrong, normal distribution. I still didn't get it right. Right click and there we go. Cumulative distribution function. Okay, so we said that's capital Phi of x. And we said that that is nothing more than a cumulative distribution function with mean 0 and standard deviation 1. Okay? All right, so there's my standard cumulative distribution function. And now let's go ahead, whoops, and prove Theorem 1, right? Which we said was we do this by direct substitution. Okay, so in other words, let's just show that, okay, the cumulative distribution function for a arbitrary mean and standard deviation, right? That was this expression here, right? And we claim that that is nothing more than the standard cumulative normal distribution function, right? But instead of passing in x, I'm going to pass in as an argument x minus mu all over the standard deviation, right? And if you shift enter that, it's true. So yeah, just directly substitute and show that this works. Okay, so with this information in hand, we can go back to the board and compute the probability that a sample from an arbitrary Gaussian will assume a value within any given interval. All right, so now let's move on to how about Theorem 2. which is nothing more than basically a restating of how a cumulative distribution function works. Namely, it's going to say that, all right, if I want the probability that some function or some sample, let's call this maybe capital X, right? I want this to be in between a specific value or between a specific interval. How about it's got to be strictly greater than B and strictly greater than A and strictly less than or equal to B here, right? And we said, okay, the way this works here is again, just graphically, the way to interpret this here is, sure, you've got some probability distribution function f of x, right, versus x, and I want to understand what's the probability that the sample falls between A and B. Well, that's just the area under the curve here, right? And we saw now that with a continuous probability distribution function like we're dealing with right here, it's the greater than, equal, less than equal. It really doesn't matter, right? You could arbitrarily add that, and that doesn't change the area under the curve for continuous distribution functions here. But in this case, we saw that, okay, this is really simple to get to, right? That was the whole idea of what a cumulative distribution function did. So we can just say that this is f of b, right, minus f of a, right? And now, using Theorem 1, we saw that, okay, capital F is just related to the standard Gaussian, standard cumulative normal distribution here via this. So all you got to do is substitute, make substitutions, right? So I can say that, all right, this is the same thing as capital Phi of B minus mu all over sigma minus capital Phi of A minus mu all over sigma, right? That's the exact same thing. And finally, we saw that, okay, capital Phi was related to the error function through this relationship, right? Again, let's just make one more substitution. Substitute this into this so we can say that, all right, the other way that you could write this is you could say that this is nothing more than, by the time you simplify this, I can pull the 1/2 out to the front, I guess. Well, I'll tell you what, let's not pull anything out. Let's just do this term. This term right here is, let's just make the substitution, right? It's 1/2, 1 plus the error function of 1 over square root 2 times b minus mu all over sigma. This, okay, minus, again, make the substitution for this. It's 1/2, 1 plus the error function 2 times a minus mu all over sigma. There we go, okay? So this is what's really actually pretty helpful, right? This version of it right here. Because, like we said, this is what I want to compute. Someone hands you a Gaussian distribution with an arbitrary mu and an arbitrary sigma, and they say, what's the probability that your sample is going to land between A and B? Well, here it is, and it's written with respect to the error function, which we said we know that most computer packages will provide a implementation of this, right? So let's look at an example of this. Tell you what, give me a second to erase the board. I'll move this formula down in the corner because we're going to want to keep it, and then let's run through an example of this. All right, so I moved our Theorem 2 results down here to the bottom, and I wanted to point out I made one mistake in the previous note. I forgot to close this parentheses on both of these terms, so this is the correct expression. I think the one thing I missed in the previous one was this large parenthesis on either side. So if you want to correct your notes, make sure you add that here to close off the overall, to make sure the entire thing is multiplied by 1/2. So anyway, long story short, small little typo I just wanted to point out, okay? So that being said, let's go ahead and I would like to apply this to an example here. Let's go ahead and look at a Gaussian / normal distribution with this mean and this standard deviation. So again, just to sketch this, what this means is that we've got a distribution which is centered around 0.8, okay, and has a standard deviation of 2, so I don't know, it's going to look something like this, right? It's going to be centered around 0.8. And now what I want to do is I want to compute 3 different parameters. One, let's compute what's the probability that any sample drawn from this distribution is below 2.44 or greater than or equal to 2.44. Then we'll look at one where what's the probability that you're above 1, and then finally we'll look at the probability that you fall between this region, okay? So let's start out with I, okay? So So the probability that x is less than or equal to 2.44, okay? So again, graphically what that meant here is that we're going to find the point 2.44, I don't know, maybe it's out here, I'm kind of making this up, and now all I need to do is I need to integrate between minus infinity up to here, right? Because that's all the area underneath the probability distribution function, or we said that's exactly what the cumulative distribution function gives us, right? So I just need to pass in 2.44 to my cumulative distribution function, and actually via Theorem 1, we saw that, all right, that is basically going to be, it's going to be just one of these expressions, right? Because I only need half of this. So it's going to be 1/2 times 1 plus the error function, 1 over root 2 times, okay, the parameter I'm looking for here is, this is 2.44, right, minus the mean, which was 0.8, all over the standard deviation, which was 2, okay? That closes this, wait a second, I just want to make sure I get this right. Did I miss a parenthesis in my notes? I might have missed a parenthesis. Okay, so because this closes this closes this, then that closes that. There we go. Okay. Okay, so at the end of the day, you look at this, you see that this is just a number. You just need to run over to Mathematica and plug this in, and we'll do this in a second, but why don't you take my word for it that if you do this, you come out with a probability of 0.7939. Okay? So there's about an 80% chance that any sample that is drawn from this distribution is going to be below 2.44. Okay, let's go ahead and move on to the second example, II. I would like the probability that x is greater than or equal to 1. Right? Let's do a little trick here to make this a little bit easier. I think everyone would agree that the probability that a sample is below 1 is basically the complement of the probability that a sample is less than 1. Right? It's the same thing. And now we're back in the exact same arena we were kind of in step 1, okay? Except I've got this 1 minus hanging out in front. This is 1 minus the cumulative distribution function of 1, right? Which is now 1 minus, we're going to apply our theorem again, and this is now, let's make this a big bracket here, 1/2 times 1 plus the error function of 1 over root 2 times 1 minus 0.8, right? All over 2. Close, 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 close. Something like that, right? So you end up with all of this, and this is just going to be, I think you come up with a number of 0.4602. Okay, so the 46% chance that the sample is larger than 1. Okay, great. Let's do our last example, III, right? I want the probability now that this sample is between a region of 1.0 and 1.8, right? So now graphically, that's coming over here and finding the point 1 and 1.8, and now just integrating this thing between those two regions. Or we saw earlier that this is nothing more than the difference of the cumulative distribution functions of the higher value minus the lower value. Right? This is the same thing, and this is exactly our expression down here. So I guess we can write that out one more time for completeness. Right? So this is 1/2 times 1 plus the error function of 1.8 minus 1. Or sorry, whoops, 1.8. I got too excited. 1.8 minus the mean. Right? The mean was 0.8. Right? All over the standard deviation. Close, close this. Okay, minus 1/2 times 1 plus the error function of 1 minus 0.8 all over 2. Close, close. Something like that, right? Yeah. Okay, great. And again, you plug in all these numbers here, and I think you end up with a 0.1516. Great, so there's a 15% chance that it falls within this region. Great. So, give me a second to erase the board, and let's extend this idea maybe one step further. All right, and actually before moving on, let's just go ahead and double check our answers. Okay, so the first one, I think for part A, was we were interested in what's the probability the sample is below 2.44. So we said that was just what our cumulative distribution function, capital F did. Again, we had a mean of 0.8 and a standard deviation of 2, and I think we said this was around 80%. And yes, indeed, that comes out. And we said that via Theorem 2, we said that this is, or actually, excuse me, Theorem 1, right? We said this is the exact same thing as 1 plus the error function of 1 over root 2. Times the sample, right, or the value of interest minus 0.8 minus the mean, and all of this was over the standard deviation, right? So this should be the same thing. Yes, and there we go. And then why don't we go ahead and check part 2? I think that we said that I wanted the sample, probably the sample was above 1, which was the same as 1 minus the sample being below 1, right? And then we said that, okay, all I need to do is just put 1 minus this entire thing, and again, change the value from 2.44 to 1. And I think we should both get, yeah, here we go, 46%. Perfect. And then the last one, I think, is we were interested in what was the probability that the sample fell between 1.8 and 1. So that's just the difference of the cumulative distribution functions, 1.8 and 1. Right? And then we said this was the same thing as if we had used the error function and gone between 1.8 and 1. And I think we said this was somewhere in the neighborhood of 15% or something. And yes, there we go. So both of these are the same. So yay, they all work. All right, so let's take this idea and the ability to compute the probability a sample falls between an arbitrary interval here with our normal distribution and look at the 1, 2, and 3 sigma limits. And what these are is, it's actually pretty simple to think about. If you, again, look at, you've got some Gaussian distribution, right? And it's got some arbitrary mean mu, and therefore it is symmetrical about this, with some standard deviation measuring the amount of spread of this distribution. What we would like to compute is, let's compute what's the probability that a sample falls between one standard deviation in either direction of the mean, okay? So let's call this maybe like a 1 sigma limit, right? And we can then also look at, well, tell you what, let's start here. Let's just go ahead and compute this. So we can see, again, all I want to do is I want to integrate the area under this curve. So all we're looking for is what's the probability that a sample x, well, let me give it a little bit more room, that this sample x, right, is greater than it's mu minus sigma, right? That's the lower limit. That's this point right here. This point is mu minus sigma, and the upper point here is mu plus sigma. Would everyone agree? Okay, so I want to know what's the probability that it is above mu minus sigma, but less than or equal to mu plus sigma, right? So that's exactly what we've got right here. You can actually go ahead and plug this in. So in the interest of time, I don't think I want to just go ahead and do this. In fact, we'll go over to Mathematica and look at it in a second. But you're going to get some value here by just plugging that in. And what's interesting is that when you plug that in to this expression, it doesn't matter what the mu and the sigma are. What this number comes out to be is it comes out to be 0.682. Okay, so let's think about this. What does this mean? This means, if you think about this long enough, that about 68%, or I think, you'll hear people call this, roughly the 2/3 rule. That 68% is pretty darn close to 2/3 here. What this means is I don't care what your Gaussian is, it can have any mean and any standard deviation, but about 2/3 of the samples are going to fall within one standard deviation of the mean here. Right? That's pretty awesome. We can extend this idea to maybe looking at, how about like a 2 sigma limit, right? Like what's the probability that the samples will fall within 2 sigma? So this distance now is 2 sigma in either direction, right? So this is 2 sigma plus and 2 sigma minus. So now we see that the idea is really simple. Again, I want to integrate the area under now this larger curve, right? And all I have to do is I have to move my integral limits right? Now I'm looking at the lower point being mu minus 2 sigma, and the upper point here being mu plus 2 sigma, right? So again, the probability now that a sample is greater than mu minus 2 sigma and less than mu plus 2 sigma is, again, just plug into here, right? And again, you do this, and now you get a number of 0.9545-ish. So again, this is really interesting. So it's saying that about 95% of all of the samples fall within 2 standard deviations of the mean. So by the time you move 2 standard deviations out, you're capturing almost all of the samples. And again, let's bump this up maybe one more time, right? Let's look at a 3 sigma limit. So I want to look at going between mu minus 3 sigma to mu plus 3 sigma. Again, all you do is plug it into this expression with a slightly different a and b, right? And now what you end up with is a number of 0.9973. Okay, so this means 99.7%. So practically all of the samples now are within 3 standard deviations of the mean. So this is actually very helpful. So it helps you understand with a Gaussian, it is very difficult, almost impossible for a sample to fall more than 3 standard deviations out of the mean. Okay, so tell you what, to make sure I didn't make this up, let's run over to Mathematica and plug this in and make sure these are the same numbers we get. All right, so let's go ahead and verify the 1, 2, and 3 sigma limit results that we just got, right? So we said that the probability that a sample falls between a region A and B is given by this, right? For an arbitrary Gaussian with arbitrary mean and arbitrary standard deviation sigma here, right? So this is, again, just using our cumulative distribution function definition, right? So here's what it is. This is basically what we had on the board. So now all we want to do is I want to see how about the upper limit is mu plus sigma and the lower limit B is now mu minus sigma. And what's fascinating about this is if you plug that in, look at this, the mu and the sigmas disappear, right? It doesn't matter what the mean and the standard deviation is you end up with this expression here. And again, this is just a number, so if I just say /n to get the number, here's our 2/3, right? You get your 68%. Now, that's our 1 sigma limit. Let's look at the 2 sigma limit. So I'm going to change this to now 2 sigma, 2 sigma. This should be now our 95% result. Yep, and there we go, 95%. And finally, the 3 sigma limit is if I go one more, this is our 99.7. Is practically all of the samples fall within that region. While we're here at the computer, I wanted to show you another kind of interesting example showing how Gaussian distributions actually show up quite a lot in engineering and science. So I've got some data that I collected from a robotic sensor which measures heading angles from the sensor to some target here. So I've got this in this mat file. So let's just go ahead and write a quick script to look at that data. So let me go ahead and say I'll load the heading data.mat. And let's just run this to start, and we can see what it does. It generates, and it's got data, like I said, the time and the samples at a given time. So let's just go ahead and, how about plot the data, the heading data, to start. So I'll just say plot t psi, and let's make this a little bit fatter so we can see this. Okay, and the x label is obviously time in seconds, and then the y label is going to be the heading angle psi in units of radians. Okay, and let's turn the grid on, and let's just go ahead and run this just so we can see what it looks like. And I'll pull this over, and here you go. So here's some real sensor data that actually came off an actual unit. And you can see it's a noisy signal, just like you would expect, right? In real life, the object that you might be targeting might not be moving. And you can see it's probably here around a heading angle of 2.81 radians, but there's quite a bit of noise on top of this. What would be cool is we should see, what does this noise look like? What's its distribution? How far away is it from the average value? So let's come back over here, and what we can do is let's go ahead and compute the mean and variance of the signal. So we know that the mean and the variance is defined for any signal, right? It doesn't have to be Gaussian. In fact, there's nothing that said that Gaussian or normal distributions come into play here at all. So I'll get the mean by just calling MATLAB's mean function, and then I'm going to get the variance using the var function. So var, if you come over here and say help var, it says that it gives us the variance of a vector. I actually don't want the variance. You remember up here in all of our examples, we were playing with standard deviation. So I'm going to take the square root of this variance to get sigma, right? So there we go. This gives us the mean and the standard deviation. So let's go ahead and actually, I'll tell you what, I'll remove the semicolon so we can see what the results are. And we see, yeah, the mean of this signal is about 2.8 radians, and sigma is about 0.0069. Well, what does that really mean for us? So what we can do is, let's see, does a Gaussian distribution describe this signal accurately? Right? So what I mean here is, let's go ahead and calculate what is the Gaussian that's associated with this. So let's go ahead and create some x values, and I'm going to say linspace. We'll make the samples go between the minimum heading angle that the sensor data has to the max value that the sensor data has, and let's use maybe 100 spaces. So here's my x values, and now the Gaussian distribution, we know it's just, well, what is it? It's 1 over sigma times square root of 2 times pi, right? This whole thing times e to the minus 1/2 times the quantity x minus mu, and I guess I got to put this in parentheses here. This all over sigma, this whole thing squared. So I'm going to have to dot star this. Let me move this over so we can see everything all in one line. There we go. Okay, so I think that should be the Gaussian. Let's go ahead and plot this to look at it. Plot the Gaussian. Okay, so again, this is the Gaussian that we fit with the mean and standard deviation that we measured from the data. So I'm going to say figure plot x f of x, and again, let's make this a little bit fatter so we can see this. So the title of this is the Gaussian calculated from the distribution of psi. Right? So the x label is going to be psi values, right, in units of radians, and the y label is going to be the probability distribution function f of x, right? So let's turn the grid on. Let's go ahead and run this, and here's our Gaussian distribution, okay? Okay, let's maybe do one other thing. We should verify that this Gaussian is a valid Gaussian, that we didn't screw something up. So what we should maybe do is, let's verify that the integral of the Gaussian is 1, right? So let's just integrate this signal f of x, okay, with respect to x. Okay, so to do that, MATLAB has a couple of integration routines. Let's just use trap z. Trap z is an integration technique, right? That gives us a trapezoidal numerical integration, so that's what I'm interested in doing. So let's say x and f of x, and this better come out to be something close to 1. So let's just run this again, and here we go. Yep, 0.9987, that's close enough to 1, so I will believe it that this is a valid probability distribution function, okay? So now, here's the cool part. What we want to do is, let's go ahead and also plot a histogram, how about of all of these signals, so we can see the frequency of all of their samples, okay? So let's start a new section of the code here, and let's say I want to plot a histogram of psi. Okay, so let's first, I'll make some bins, how about? Let's go from linspace, from, again, min of psi to max of psi, and let's use 20 bins for our histogram, okay? So we can just go ahead and say figure hist of, I guess we're going to need psi, and we're going to give it the number of bins here. So these are the bins that we want. So let's go ahead and say, I think that's probably enough. So let's run this again. And here's the histogram that we obtain, and here is the Gaussian distribution. And if you notice, they look really darn similar. In fact, I wish we could overlay the two. In fact, tell you what, let's write a little extra code to overlay the shape of this Gaussian over this histogram. Again, notice that we're going to have to do a little bit of scaling here, right? Because this Gaussian is a probability distribution function, and a histogram is just counting the number of instances here, right? So the y-axis, they don't match up, but the x-axis should, right? They should make the same amount of sense. So let's do this. Let's scale this Gaussian distribution by some alpha value to make it so that we can just plot it on top with the same y values. So let's just go ahead and do that. So let's calculate a scaling factor, let's call it alpha, to allow the Gaussian to be overlaid with the histogram. Okay, so let me see how we're going to do this. I think what we need to do is come back to the histogram, and we actually need to ask for, if you look up the help on histogram, it says right here that if you ask it for output arguments n and x, it will also return the position of the bin centers of x along with sort of the heights. Okay, so that's I think what we want to do. So let's say nx like that. So now we have the heights, and tell you what, let's get rid of this figure because I'm going to want to plot this later. Okay. All right, and now what we want to do is let's scale this. So alpha is going to be a scaling factor, so we need to look at the maximum height of the bins versus the maximum value of the function. There we go. So I think this alpha is going to be some number that's much greater than 1 here. It should basically be the ratio of, it looks like around 410 to 60. So whatever that number is, I don't know, 3-ish something. Well, here, I'll tell you what, instead of me guessing, let's just run this and let's see what it looks like. So alpha is, 7. I was way off. Okay, so anyway, what we can now do is plot the Gaussian, and I guess maybe we should say is quote-unquote Gaussian, right? It's no longer the Gaussian distribution. I'm going to scale it to fit over the histogram. So let's just start a new figure, and I'm going to, first let's plot the histogram, so of psi and the bins. Okay, and then let's turn the hold on, and then we'll plot the quote-unquote Gaussian, right? This is the Gaussian, but I'm going to now scale it by alpha so that it sits on top of it. And maybe let's make this a dashed red line, and again, let's make it a little bit fatter so we can see this. And now if we run this, look at this. This is pretty cool, because if you think about this, look, overlaid, the Gaussian distribution fits the real-life data extremely well. And again, we didn't make up this data. We really pulled this off an actual sensor unit, and you can now see that the sensor model, it mostly registers, if we look at the raw data here, right, it mostly gives you the mean, right? But according to our discussions on the 1, 2, and 3 sigma limits, we can see how noisy this signal is, right? We know that most of the signals, 2/3 of the signals, are going to fall within, whoops, oh great, now I had a big, oh great, MATLAB is going to crash on me. Ha, that's hilarious. Well, anyway, most of the signals, 2/3 of it will fall between plus and minus 1 sigma. So within 0.0069 radians, I mean, what is that in degrees here? So let's see, this is rad 2 degrees of sigma here. Okay, so this is a pretty good sensor, right? Because 2/3 of the sample, it's within, 0.4 degrees of the actual value. And again, our 2 sigma value, we know this is going to get 98% of it. So less than a degree variance. And pretty much I can virtually guarantee that the sensor is never going to report a value more than 3 sigma out of the limit. So you could almost say that this sensor, let me pull out the figure. Whoops, sorry. This sensor here, right? It's accurate to within, I would be confident to say plus or minus 1 degree here, because I know that there's almost virtually no chance that it's going to report an erroneous signal that is past 1 degree from the mean. All right, so we saw how this was really interesting and useful and how Gaussian normal distributions show up in real systems. Well, the next question you might have is, well, could I make my own Gaussian distribution samples? Like, for example, if I wanted to simulate this signal or add Gaussian noise to a signal, and you totally can. MATLAB has got a couple of tools that'll help you for this. So first, let's say help rand. And rand by itself is a uniformly distributed set of random numbers between 0 and 1. So this is not exactly what we want. We want a Gaussian distribution instead of it being flat. Well, if you come down here and you look at C, also there's a randn. So randn, if you go ahead and click on that, you'll get the help page for randn, which is now, this is what we're looking for, a normally distributed set of random numbers. The only thing that maybe we want to call to your attention right now is that randn will actually draw values from, here it is, right here, a standard normal distribution, meaning the mean is 0 and the variance is 1, therefore the standard deviation is 1. So it's not going to get you a arbitrary Gaussian. We're going to have to do a little bit of transformations to make randn give us what we want. So tell you what, let's jump over to the board and look at how do I transform a standard Gaussian to an arbitrary Gaussian. All right, so we know that the function randn in MATLAB is going to give us a distribution with mean 0 and standard deviation of 1. So we would like to now translate this to an arbitrary mean and arbitrary standard deviation to simulate a random distribution of a more general type. So to do this, if you remember a previous discussion, we had a theorem which talked about the transformation of mean and variance. So in other words, what it basically said that if you had a random variable, if a random variable has mean mu and variance sigma squared, then the random variable, let's call it, how about x star here? I guess we should have said this random variable, maybe I should have said the random, let's call this random variable capital X here. So if I take capital X, okay, take the random variable and I multiply it by some scalar a2 and then I add a constant a1 here, what this is going to do, it's going to transform the mean and the standard deviation of X to a new mean and standard deviation where this X star has mean and standard, and variance of the new version, which is, let's call it mu star here. Okay, so mu star is going to be related to mu through this. And finally, the variance star is going to be the original variance times a2 squared. Okay? So again, the way this is helpful to think about is we're able to generate samples X using randn, which are going to have a mean of 0 and a standard deviation of 1. I would like to transform it so that it has another mean and standard deviation of something else and something else. That are these star values. So what I need is, let's back solve for the A1 and the A2 that are going to make that feasible here, right? So let's just go ahead and say solve for A1 and A2. So if you just solve this for A1 and A2, you would basically get, at the end of the day, A1 is going to be negative sigma star over sigma times mu plus mu star. And finally, A2 is going to be sigma star over sigma. Okay? So let's box these up because these are helpful. The algorithm now that we're going to use to make this transformation here is you could basically say, let's write this in kind of quasi-MATLAB. Let's say draw sample from randn, right? And make a note here that this sample has mu of 0 and variance of 1. Okay, so we're going to do that, and I don't know, we can call this thing X. So something like X is, you know, something like randn of yada yada yada, right? Whatever arguments you want. Okay, so this will give us one or multiple samples with this particular variance. Now what I want to do is choose what mean and variance we want. So in other words, you get to pick, all right, I want to simulate this thing to have a mean of, I don't know, let me make up something. How about, what did I use? Here, minus 15.5. So I don't want the mean to be at 0. I want the mean to be at minus 15.5. And I want a variance of, what was it? What did I use? I used 3.5 squared. So it's standard deviation of 3.5. This is what I want the new samples to be. So what I can now do here is go ahead and compute A1 and A2 using our equations over here. So just basically plug those in here because you can see now you've got everything you need. You know mu is 0. You know sigma is 1, right? Since you take the square root of 1, you get 1. You know what you want the mean to be, that's mu star, and you know what you want the variance to be, that's sigma star. So you've got everything you need to calculate A1 and A2. Now what you can do is go ahead and transform samples, the samples capital X to X star. Right? Using this relationship we had here. So finally, you know, you get X star is just going to be A1 plus A2X. And now this set of samples should be distributed according to the mean and the standard deviation that we specify here. So let's run over to MATLAB and just verify that this works. All right, so let's just start ourselves a new script here and go ahead and see that this works. So first, let's go ahead and draw, how about 500 samples from a standard normal with mean 0 and standard deviation 1. We're going to use the randn function to do that. So again, let's read the help documentation on this. And we see that randn, we can go ahead and use, here we go, randn, we'll give it the number of rows and the number of columns to get a matrix of samples. So let's do this. How about randn of 1 by, how about 500, right? So this is going to go ahead and give us a bunch of samples. Let's call them R, okay? All right, so if I run this, you see we get a whole bunch of samples, but all of these samples are distributed between, with a mean of 0. So if I want to convince myself of that here, let's whoops, not plot, let's histogram these guys, okay, and pull that over, and you see, yes, they are all centered around 0, and they sure stick within 3 sigmas of that mean here, right? They don't go past plus or minus 3. It'd be virtually impossible to do that. Okay, so now what I want to do is let's go ahead and transform this, right? We want to transform this to an arbitrary Gaussian distribution, right? So let's go ahead and compute the parameters we need. So first of all, we know that the original Gaussian has a distribution, a mean of 0, right, and a sigma of 1, right? This was the original parameter. So now what I need to do is choose what is the desired mean and standard deviation, right? So mu star, we said, let's make this, how about minus 15.5, and the sigma star, let's make this a little bit larger, so 3.5, okay? So now what we can do is calculate A1 and A2 via the equations we had on the board just now. So A1 is going to be minus sigma star over sigma times mu plus mu star. And then A2 was going to be sigma star all over sigma. Okay, great. So now what we can do is we can actually go ahead and perform the transformation. So R star, or these new random samples, is going to be A1 plus A2 times R. And now what we can do is let's plot this one here. So I can say figure hist of R star. Actually, you know what? Let's plot these two on top of each other. I'm going to delete this. Let's come down here, and I'm going to make a subplot 2 by 1 by 1. Let's plot the original one, or histogram the original R, and then underneath of it, let's make another subplot, and we'll look at R star. Okay, and whoops, all right, I spelled something wrong. Sigma instead of signa. There we go. Okay, sigma. There we go. And if I run this, you look at this, and
Yes, this looks like it worked. Right here, the top plot is the original distribution. The bottom one, yeah, check this out. The mean has now shifted to minus 15.5, and we get the appropriate spread. In fact, instead of just eyeballing this on a histogram, let's just go ahead and, how about, compute the actual sample mean and standard deviation that we end up with. So what I'm going to do here is just say, let's get mean of R star, right? And let's get the variance of R star. And let's go ahead and take the square root of the variance so that we can get the actual standard deviation. So we're hoping that this is minus 15.5, and this here should be somewhat close to 3.5. So again, if we run this, you see, yes, look at that. That is exactly what we get. So this is a good way to transform an arbitrary, to transform what randn gives you, which is a normal distribution between with mean of 0 and standard deviation of 1, to any distribution. So now you can use this signal R star to simulate an arbitrary signal with appropriate statistical distributions of parameters that you're interested in.
All right, and no discussion of Gaussian and normal distributions would be complete without a discussion on the central limit theorem. So the central limit theorem basically states that in some situations, and we'll see that there's actually quite a few situations that fall into this category, what this basically states is that the distribution of sample means will approximate or converge to a Gaussian regardless of the distribution used to generate the samples. Okay, and I'll just leave it at that. Feel free to, this is a very sort of hand-wavy definition of the theorem. I think it's easier to see it by example. So first, let's go ahead and define our samples. So the notation of this is, let's just say you've got a sample. Let's call this thing capital X, and this is a sequence of, multiple observations like x1, x2, all the way up to xn, capital N here. Let me write this a little bit better, kind of butcher that, capital XN here, right? So this is a single sample with n observations. So it's like you flip or you roll a die and you roll it, capital N times. And that's one experiment or one sample, however you like to think of that, okay? Now, with this one sample, which is made up of multiple observations, what we might want to do is you might want to calculate what's the average of all of these observations, or calculate the sample average. So the sample average, let's call this S capital N. So if you take n observations, the average of these n observations is, well, it's really easy. You calculate the average of this, right? That's just x1 plus x2 plus all the way up to xn, and then divided by n, right? So here's your sample average. So it's probably no surprise to you that as n gets bigger, right, this sample average is going to go to the mean of whatever distribution was used to sample or to obtain all of these samples. So what's maybe not so obvious and what is a little bit surprising is that the shape of all of these averages, if we repeat this multiple times and we get more than one sample, like let's say we do m samples, what you'll end up with is you'll end up with a distribution that appears normal regardless of how these observations were generated. So maybe what we should do is let's write this down here. So what we're going to end up with here is that the mean is going to go, let's call this, how about mu x? of all of these distributions, this is going to go towards the mean of the distribution used to generate this. And furthermore, we said that the normal distribution is going to have a standard deviation, which is going to look like the standard deviation of the original whatever was used to generate these observations divided by the square root of n. Okay, so again, I think it's easiest to look at this as through an example. So let's do a very simple one to start off with. How about let's look at a uniform distribution. Okay, so what we're saying here is that we have this uniform distribution which looks like this. So let's say here's f of x versus x, and let's say it's between 2 and 5, and it is just like this. So we've got some process or whatever, some game that we're playing or some experiment that we're doing that when you do a single observation or a single trial of this experiment, you have a probability, you have an equal probability of getting a sample anywhere between 2 and 5, right? And I think to make sure this area under the curve is 1, I think this has to be what? This has to be a third, right? Okay. So you have an equally likely chance of drawing a value between 2 and 5. So this distribution, I mean, this does not look Gaussian, right? There's no bell shape to this. This is completely flat. What's interesting, though, is again, from our previous discussion, we know that you can calculate the mean of this distribution, right? The mean of this distribution, this uniform distribution, is just if this bottom part is A and this top part is B, this is A plus B over 2, right? So in this case, the mean of this is 3.5, right? And furthermore, you can also calculate the standard deviation of this uniform distribution as being, I think it's 1/12 A minus B squared. So in this case, it's 0.75, okay? So you could probably imagine that we can go ahead and let's conduct one experiment or get one sample which is made up of, say, how about n equals 4 trials or 4 observations. So let's start with, how about n equals 4. So this is the number of trials or observations, etc. Right? So let's get one sample. So here's sample 1. So sample 1 is, I just need to draw from this distribution 4 times. So let's do this, and I'm going to make something up, but you should equally be able to get a number between 2 and 5. And I did this, and let's say I came up with 4.44, 4.72, 2.38, 4.74. Right? Okay, so here's one sample made up of n equals 4 observations here, right? And what I can do right now is I can calculate what is S4, right? Which is basically the average of this sample here. So an average made up of 4 observations. So again, that's just easy. You just calculate the average of all of this. I think what you get up is 4.07, something like that. Okay? So what I can do now is let's go ahead and start ourselves a little histogram. Maybe where can I draw this? I'm not going to run out of space. I will. Let's erase this. Okay. So what we can do here is what I want to do is plot frequency and basically versus average, or sorry, this value S4, right? S4 value. Right? So we know that it's going to be, the average has to be somewhere between 2 and 5 or something, like this. Okay? So in this case, we got 4.07. So I'm going to put, here's one. Here's one sample here. Right? So with frequency 1, I got something in this bin. Right? So I could bin up this sequence into however many bins I want. And here's one. Okay? It's the black one. Okay? Let's get ourselves another sample. Okay? Let's do this again. So how about sample 2 or trial number 2, however you want to think about it. So again, I will draw from this 4 different times. Let's say I get 3.90, 2.92, 2.84, 3.64, whatever, right? I just draw 4 uniform numbers. And again, I'll calculate the sample mean here. So again, S4 for this sample, number 2, came out to be something like 3.17. Okay? So great. What I'll do then is let's come over here and we'll plot that. I don't know where 3 point, maybe it's here or something like that, right? So here's frequency 1 here. Okay? Great. Let's keep trucking. We'll do, how about one more? So let's say sample 3. So sample 3 here in blue would be, all right, I do this again. You get 4.87, 4.89, 2.47, 4.91, okay? And again, let's calculate the sample mean here with four observations, and you get something like 4.28, okay? And maybe that falls into this same bin here, so I'll draw another one here. Now we're up to a frequency of 2 for here. Okay, so does everyone get the picture here? So we have n equals 4, that's the number of observations per sample, and then why don't we call this m in this dimension? So there's m samples. Now, what we're going to see here is obviously, this is not much of a histogram with just m equals 3 samples. We want to jack up m, and let's do this thousands, 10,000s, a million times, and let's see what does this start looking like as we increase m as well as increase n, which is the number of observations per sample, okay? And what the claim is that even though all of these samples, right, are drawn from a uniform distribution, this histogram is going to end up looking like a Gaussian curve with a mean here. So this mean here, mu x, right, of the distribution of the Gaussian, is going to be close to the mean here. And furthermore, the standard deviation of this Gaussian distribution, sigma x, right, is going to be similar to it's going to be related to the standard deviation of this uniform distribution, but scaled by square root of n here, okay? So that's fascinating. Let's run over to MATLAB and verify that this works. And then what we also want to do is we're going to show that, again, we'll do the first case with a uniform distribution, and then just to show how this works for even more ridiculous, more skewed distributions, let's also look at changing this distribution to be something like a triangle. Maybe I think it's the next example I want to look at, where you might have some kind of distribution which looks something like this, like absolutely not uniform, not Gaussian, no whatever, it's just something completely different, but still, you run through this process and we'll still end up with a Gaussian at the end of the day. So this is crazy. It's like, it's one of these things where all roads lead to the Gaussian. So let's go ahead and take a look at this in MATLAB.
All right, so let's start ourselves a new script, and first thing we should do here is let's go ahead and set up MATLAB's random number generator to act deterministically. So basically I would like it to repeat the behavior and act in a similar fashion every time I use it. So we can do this command, rng, and set it to default. So it will act similarly. Okay, so what we can now do is let's go ahead and define our distribution, our uniform distribution. Okay, so we said the lower limit was A, the upper limit was B of 2 and 5 respectively, and we know that we said the mean of this distribution should be A plus B over 2, and the standard deviation should be 1/12 times A minus B squared. And actually, I screwed this up on the board. I'm going to have to correct it again. This part that I'm highlighting, this is actually the variance of a uniform distribution. So to get the standard deviation, I need to take the square root of that. Remember earlier in the discussion where I said I guarantee you somebody's going to mess up the difference between variance and standard deviation? Well, turns out that somebody was me. So, okay, let's go ahead and run this just to make sure we've got the same numbers. Okay, yep, here's our mean, here's our standard deviation. Okay, so what we should now do is let's define the number of observations per sample. So that is n. Oops, sorry, and I said we had 4. That was our situation. And now let's go ahead and define the number of samples in our experiment. So that's m is 3. Okay? All right, so I think we've got everything set up. What we can now do is let's just run a simulation. So we're going to say for m gets 1 to big M. So let's just go ahead and sample n times from the uniform distribution, right? So we can do that using the rand function. Remember we talked about this earlier, that rand gives us a uniformly distributed set of numbers. Unfortunately, it does that between 0 and 1, but as you saw earlier, we can easily shift that to be any to have any mean and standard deviation that we want. Well, I wrote myself a function called rand2 that's going to do this. So I'm going to say rand2 goes from a bottom of A to a top of B, and I want n samples here, okay? So let's call this thing x. If I just go ahead and leave off the semicolon and run this, you can see that here's sample number 1. I think these are the numbers we wrote on the board. And then here's sample number 2, and here's sample number 3. Great, so the next thing we would like to probably do is add that semicolon back, and then let's go ahead and compute the sample mean. So I'm just going to say mean of x. This is what we called Sn, or I guess S4. And finally what we should do is probably save this sample mean. So I'm going to make a container, let's call it Sn data sub m is just going to get Sn. Okay, so at this point, I think we're probably done. By the time we drop out of this loop, what we've done is we've gone ahead and run 3 trials or 3 experiments, and we ran 3 samples. Each one of those samples had 4 observations each, and then we calculated all of the means. So what I could do is I could make a very boring histogram at this point of Sn data. All right, and again, the reason this is so boring is because we only have 3 samples, so you only have three occurrences in your histogram. So what would be more interesting is let's jack up the number here of samples. So instead of 3, let's make, how about 3,000, okay? And instead of only having 4 of each observation, maybe let's make this, how about 400? Okay, and the reason I want to increase both of these is, first, I would like to look at what does this random variable x look like. We know it should be uniform. So to convince ourselves of that, let's just look at the first sample. So I'll just say if m equals 1, let's have a figure here, and I'm going to histogram x. Okay, so what this is going to look at is the distribution of x. So let's just put a breakpoint in here and run to that point. And as expected, you look at this thing, and it's a uniform distribution, right? So here's my first sample, which now has 400 observations. And if you plot that, everything between 2 and 5 is equally likely, right? So you get this this uniform distribution. Now, what's the mind-blowing part about this is if I repeat this 3,000 times and compute the mean each time, and then I histogram all of the means, look at this. Let me take out the breakpoint, run, and continue. This is what we end up with. That sure looks like a Gaussian to me. In fact, let's increase the number of bins. Let's make this thing, how about 20 bins, right? So if I run this again, look at this. That absolutely looks like a Gaussian to me. And in fact, we can compute the parameters of this Gaussian distribution, right? So let's compute the actual parameters of Sn data, right? So I can get the mean, right, which we said was mean of Sn data, right? And then I can get the variance of Sn data. And if I take the square root of the variance, we should get the sigma, let's call it sigma actual. Let's call both of these actual. So how about mu actual and sigma actual, okay? So the mu actual, like we talked about earlier on the board, that is exactly the mean of the original distribution. So the mean of this Gaussian is the same mean as the distribution which generated any one of these samples, right? Now, the sigmas don't necessarily match up, but because, if you remember, we said that the sigma expected, right, that was actually supposed to be, what was it? It was, I'm trying to remember. Yeah, here we go. It should be sigma all over square root of n, right? So now, if you look at this, let me find my mouse and hit run again. here we go. Look at this. The actual and expected line up quite well. So this is pretty darn cool, right? What it's saying here is, again, let's take a moment to think about this. It said we had some process where all of the observations were generated from this uniform distribution, right? But by the time you run this experiment multiple times and then average everything together, you get a Gaussian, you get a normal distribution. That is incredible, right? And to make this even more incredible, let's change this uniform distribution. Let's try that triangle distribution that we were talking about earlier. So let's just come back up here and change everything. Instead of using a uniform, let's change it to a triangle. So to make it a triangle, let's just go ahead and modify some of our code here. So let's say I want to make this a triangle distribution. A triangle distribution has 3 parameters, a and a b and a c. The a is the lower limit, the b is the peak value, and the c is the upper limit. So let's do it something like this. So what we're doing here is we're saying this is a triangle distribution that goes between 0 and 1, and it has a peak value at it goes between 0 and 10 and has a peak occurring at 1. So it's way skewed to the left. And we're going to see what that looks like in just a second. Now, the mu for the triangle distribution, it's actually a plus b plus c over 3. Is how we get that. And the standard deviation for this is actually, it's quite a bit more complicated, but not that bad. So it's a squared plus b squared plus c squared minus a times b minus a times c minus b times c. All of this, whoops, come on, I got to get my parentheses wrong. All of this over 18. That is actually the variance. So to get the standard deviation, I need to square root this thing. Okay, so let's set that up. Now let's go ahead and look at some of our other parameters. So again, I guess we can kind of reset this if we want. Let's make these small again, and we'll look at varying them for this distribution. Okay, now I need to sample n times from the triangle distribution. Okay, so to do this now, I guess we can get rid of this line. We're going to make use of MATLAB's makeDist function, and I'm going to say I want it to make a triangular distribution with the parameter a of what we had earlier, with the parameter b of what we had earlier, and a parameter c of what we had earlier. Okay, let's call this thing something like PD. And then I'm going to say x is going to be random, and I'm going to say use the triangular distribution and make a 1 by n set of samples here from that distribution. Okay, so that's cool. And then I think everything else is pretty much the same at this point, because all we're doing is we're changing the distribution we're sampling from. Actually, tell you what, let's crank this number back up. Let's make this like 4,000. That way we can see the distribution to start with. And here it is. It looks triangular to me. In fact, let's make this also 20 bins, so that'll make the histogram look a little nicer. Let me run this again. Okay, look at this. Here is one sample, and again, this doesn't look Gaussian at all, right? It's way skewed to the left. The mean of this, right, is at 3.6. It's not halfway, right? It's skewed off to the left. Okay, but that being said, same thing happens if we go ahead and run this some more. Well, actually, right now this is not going to work very well because the number of samples we have is only 3. So again, our histogram of all the sample means are super boring. So let's crank this number up. Let's run this thing. How about 3,000 times? Oh, whoops! I'm missing a semicolon. Hold on. Let me break out of this. Let me put the semicolon back here so we're not suppressing the output. Run this sucker again. And okay, here we go. Here's the first sample. And now again, look at this. Gaussian distribution comes out of it. So it doesn't matter if it's uniform. It doesn't matter if it's triangular. It doesn't matter if it's some crazy multimodal distribution which generates all the overall samples. When we go through looking at all the sample averages, we get a Gaussian distribution coming out of this. Of course, this only works if you have a reasonably high number of n. So for example, if I change this, like let's go back down to 4. Let's only have 4 observations per trial, but we'll still run 3,000 trials. So now if you run this, you know, this thing, it looks still a little bit left skewed, right? But as you increase this, let's go up to now, how about 40 samples? It starts looking more and more Gaussian. So in fact, you know, as you crank this thing up, we basically recover, like we were saying earlier, we come up with the Gaussians that we expect. And again, the actual variance and standard deviation of the experimentally determined Gaussian is very, very close to the expected value, or the expected value means something very specific. The expected standard deviation, right? Both of these match up quite nicely here. So this hopefully gives you a little bit of an insight of why Gaussian distributions are so important and how come they almost like naturally occur because of the central limit theorem, right? It says it doesn't matter what type of distribution was used to generate these variables or draw these samples. If you calculate the means and then you start looking at the spread or the distribution of those averages, you get Gaussians. So this is why Gaussians just show up in nature and show up in engineering and science all the time, right? It's this concept of like all roads lead to the normal distribution.
All right, so I think this is a good spot to leave it for our discussion of Gaussian/normal distributions. If you're interested in learning more, I hope you'll stick around and join us at our next video where we're going to actually be discussing multivariate or multivariable Gaussian distributions. If you think about it, right here, all the discussion we've had was for a single dimension, right? For a single dimensional probability distribution function. Well, what if this random variable, instead of taking on just a single value, it took on multiple values like a vector, right? Like instead of just being the distance along a road, what if we're looking at the position of a vehicle in the plane or in 3 space, right? And that distribution could be distributed Gaussian, in a Gaussian or in a normal fashion. So that's what we're going to talk about at our next discussion. All right, so with that being said, I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll down a little ways and click on that subscribe button, it really does help me continue making these videos. And I hope to catch you at one of these future videos. So until we talk again, I'll see you later. Bye.